I chose to attend because there are other talks that I think just being there in person really helps you engage and connect with people who have similar interests and even different perceptions. So it's just nice to be here in person.
Hello everyone, welcome to my talk. I hope you have had a great conference thus far. And today I'll be talking about implementing reflection using the techniques that are available to us right now. But before we begin, I want to, could I see a quick show of hands of everyone who knows what reflection is? Okay, that is most of the room. And of those people, do you already have some problem or something that you would like to implement using reflection? Okay, that's around half the room. So it seems I'll be preaching to the choir today. But let's get started. So I am Maiko Steeman. I'm a tools and engine programmer, and I work in the AAA video games industry. So I previously worked at Creative Assembly, recently joined Guerrilla. And I would like to explain why I am here talking about reflection. Because for me, it's been a much longer obsession than that. Because even before I worked in the industry, I was, when I was making games at university and even before that, I already had this this desire to be able to just iterate over my members, right? I just wanted to have my object, get each field and just dump it to disk, right? At that point, I just wanted to make a quick and dirty save and load system, just dump my game state to disk. And that was even before I knew the term reflection existed. I already knew I wanted something like this. Over time, of course, I started to learn the actual definition of reflection, and I started exploring different techniques to actually implement something like this. Again, using the techniques that were available at that point, with differing success. So that is what I'm going to be talking to you about today. I'm going to talk about how you can implement the reflection right now, using all of the knowledge that I've gained in the process, and kind of going to a final conclusion of having a module system that works, of having a reflection system actually powered by modules, which you might not expect, which solves most of the downsides of all of the other techniques that are currently out there. So the structure that this talk will have is, first I'll give you a quick overview of what reflection is. In the room, maybe there will not be many people who need it, but in general, I think it's a nice recap. It will also kind of set up the way I'm going to be thinking about reflection. In addition, I will talk about some of the use cases that I have, which I find really powerful to use reflection for, to hopefully get you excited to try and use reflection yourself. And finally, we'll go into actually implementing reflection right now, so that you, at the end of this talk, have the tools available to you so that you can start solving problems using reflection. Okay, so quick recap of what reflection is. So the simplest way I can explain it is that it's the metadata of the code that you write. So for example, here we have a small entity struct, and reflection is essentially the ability to ask the question, what members do I have? So if I ask that question right now to my reflection system, it will be able to tell me that my entity class or my entity struct has 2 data members. One of them is called health, which is of an integer type. The other one is called tag and is of string type. In addition, it will give me information about what functionality the class has. So it has the ability to eat a burger, and it can do that all on its own without any additional inputs. So that is nice, right? We can iterate over stuff, but why do we really care about this ability, right? To ask what members we have. And it turns out to actually be really nice for writing systems that don't depend on a specific ordering or specific structure of data, but they just care that there is some data in some form or another. So a clear example of this is if you want to write a serialization system. So that's the ability to take your in-memory representation of your objects and you want to flatten it down to a single either binary stream or JSON blob or something like that. So you can send it over the network, put it on disk, anything like that. So here, there's a half pseudocode example of how you can do this using reflection. So we get in, any value, right? We don't even know what type it is, and yet we can still reason about it. We can ask it about what fields it has, right? Which data members are in this object, and per object we can simply assign the value of each of those fields to a value in a JSON blob corresponding to the name of it. And maybe a bit of a more realistic example of how you would actually implement this yourself, right? The way you would structure this is that you would have some value to JSON function, right? So like the actual core serialization logic that you would like to write. You would have some set of things that you know how to concretely serialize. So probably some built-ins, right? Your integers, your doubles, your strings, things like that. And then you're able to compose your classes out of those. So you're essentially able to serialize anything that you can because you're able to recurse into kind of the compounds, right? The classes that contain these smaller things that you do know how to serialize. So I think that is quite nice, but we can even go further than this, right? We can embrace it as an extension to the type system. When I came up with this phrase, I was really happy about it. And I didn't know there was going to be 5 talks about compile time reflection this year. So it's not very original anymore, but it fits the slide very well. Because you can think of other systems that you could write with this, right? You could think about just, you write your application in normal C++, you write some data structures, and when the time comes that you want to write or implement a UI for this, instead of putting a lot of effort into binding it, you could use a simple declarative text format, for example, that can directly bind to your data model by string, right? So similar to how WPF does it, for example. It doesn't have to be UI or application related, right? You could take your library and maybe you want to expose your library as to other languages, like you want to make a Python binding. The information that you need for this, typically you would implement this manually with some glue layer, right, in between to explain what is going on between the two languages. But all of this information, right, the structure about your code, that is what reflection gives us. That's what it provides. So you're able to automatically generate these bindings to languages, not just to expose your library, but also to write plugin systems, right? If you want to have a small scripting language inside of your application, you want to expose some API, you can now do this automatically without cumbersome boilerplate. If we take a look in more detail to data models and how we can reason about how our data is laid out, you can think about automatically generating a full UI, right? This is often what editors do in the games industry. Here, for example, we have an object that has an unfold script. This is just like some script. It's not even, nothing ever says what is inside of this component. However, we already have the editor that fully understands it, and we have the ability to both view the values and edit them directly. So, in addition, you can usually replace systems that have traditionally been required a lot of manual work. So one of those examples is an undo stack, right? So the ability to press Ctrl Z and see the previous state. Typically, this was implemented using some base class. So every command, every operation that you were able to do in your application, you would manually need to write out what that is, and then also implement the undo version of that command. So there's a lot of manual work. But using reflection, right, we can actually do this fully automatically. We can take the state of our data. We can take a snapshot of that. We can then just modify our values like normal. And then after we're done, we can do a small diff between the two states of all the objects. And then the differences between those, we automatically store that in a command, leading to a fully automatic undo system. Also meaning that your undo system is relatively, it's really consistent, right? It's fully automatic. So I hope you all agree that this is kind of a cool feature, right? Like having the ability to reason about your code in your own program, it allows you to do a bunch of cool things. So how do we actually get there? I'm gonna go over it in a few steps. I'll first give you a quick overview of how I view reflection in a kind of mental model of sorts to explain how we're gonna implement it. I will mostly be focusing on, in this talk, about runtime reflection. This is not that you cannot use this technique for other compile time-like constructs. It's just that I want to focus this talk on something concrete. In addition, The type erasure techniques that runtime reflection requires, they're often necessary for kind of most of the things that you want to implement, right? Imagine that Python binding, you're gonna have to do some type erasure somewhere in between. So having the tools in your mind to be able to implement this is nice either way. So we'll go over implementing it, we'll go over some of the current techniques that are available, and then we'll go over modules and how modules actually change the compilation model, which doesn't sound like a big deal, but it allows us to get more information about the type system. And finally, we'll go over implementing our runtime reflection library. So I'll give you kind of the patterns and the tricks that you need to know to be able to fully implement that from scratch. Okay, so for implementing our reflection library, right, we're first gonna just have a little mental model of what our library would contain. From this, we need first like a kind of list of functionalities, right, an idea of what we want our library to even do. I'm gonna take our serialization example as reference for this. So as you can see, the thing that it needs to be able to provide is we need some ability to get that array of fields. So kind of one of the most important parts. And in addition to that, those fields, we need the ability to be able to query the value that field represents. So I'm going to change this example slightly to be a bit more of a practical implementation. Instead of just putting any value in here, the way we're going to be representing that any value is a void pointer accompanied by a reference to our own metadata type that we're going to implement in a bit. Just so we can, we need to be able to reason about which value we're referring to. Cool. Now that we have an idea of what we want our runtime library to accomplish, let's quickly go over what it would look like at the library level, right? How do we actually store our metadata types? So the simplest way to do this, obviously, is just to store it in a basic container. The one I chose is a simple hash map that goes from the type name to our type, so we can still query our types at runtime, depending on the name of the type. Then the actual implementation for our struct of our metadata type, right? It's a simple struct with just a few members. So in this case, we just have name, but in the future, we'll add a bunch more information. And the important parts are here that we have an array of fields and of methods. The actual implementation of this, we will figure out later. But the ideas, right, that I presented before are still valid here. This field class essentially is going to have a value function, so we can query the actual value that this specific field represents. And the same for methods, we can invoke it. And I'll already throw in that the way we're going to be filling this type registry is using some kind of function like this, right? Like this register type with a full type name available to us. We have full knowledge of which fields are actually on our type, which methods are on our type, which member functions, right? However we get that information right now, we don't have to worry about. We'll get to that in a bit. So this is kind of the interface that we're going to be representing, right? It's essentially a type erasure interface. That's most you should keep in mind. Okay, so we have a little bit of an idea of how we're going to store our metadata at runtime, right? And we have a bit of an idea of how we're going to fill that. Now let's actually gather the type information. This is kind of the meat and potatoes of any reflection library, because this is something that's not really you're not able to nicely do this right now. So to explain that, I'm going to go over the current techniques that most people use. I'm going to kind of categorize them and kind of explain why they all have like their own individual downsides. So the most obvious one and the most straightforward one to implement is to just do it manually, right? We as programmers can read our struct. We know what types it is. So we can explain it to the reflection library perfectly fine. The downside of this is that you constantly have to add these definitions, right? Whenever you change the type, you have to update your metadata representation. The other thing is that it's a bit of a cop-out, right? I was here raving on and on about like, look, you can fully automate the Python binding, you can fully do everything automatic, and then for me to just go around and say like, yes, and now the boilerplate that you're avoiding, I will shift it to filling the reflection library instead. It's not really satisfactory. So let's take a look at some automatic techniques. The first one is one that you can use today. It's a reflection technique that you can use to reflect aggregate types, essentially. You You can go over each of the types in an aggregate and you can see what it is. The technique itself uses very heavy method template programming, but it essentially uses a trick where you try to add one element after each other, and then at some point that stops failing. That will fail because you run out of fields in your type. So that's a general gist of the technique, and then you use VNA to cut that off, and then you can reflect your stuff. The downside is that this is not really flexible enough, right? You're not able to really have invariance in an aggregate struct, so one that only has public members. It doesn't involve any member functions at all. So if you want to know more about the implementation, it is kind of cool. You can, for example, watch this talk, Reflection Without Reflection TS by Fabian Giles. He gives quite a good overview of it. But let's move on to maybe something a bit more powerful. Something you might think to do, right, when you're like a bit annoyed by not having reflection like me. You're just looking at your struct definition being like, man, this is so simple. It's right there, compiler. Why can't you just give it to me? Actually, I'll grab it myself. I'll go in an angry weekend, I'll write a quick C++ parser. And this will probably work for the first week. And then every week after, you'll find new and new edge cases, because the reality is C++ grammar is incredibly complex. So maintaining this thing is a really big mess. There are some examples of projects that do it, right? So Qt's meta object compiler, it uses this technique. Unreal's header tool, for generating reflection info as well. It uses this as well. But those are also massive companies, right? And we don't really want the hassle. In addition, one of the goals I have for myself to write a good reflection library is that I would like to just get it and just implement it into my project. I don't want to have this hassle of passing back and forth these include directories. You have to make sure to sign up or to sync up all of your defines so that it's properly, it needs really deep build system integration. And I would like to avoid it if we can. Okay, so let's move on from parsing ourselves to using a proper compiler frontend. So you could use something like libclang. This will solve the problem of having this maintenance nightmare of maintaining a parser yourself. The downside of this is that it is a full compiler frontend. So it tends to be relatively slow, and it also tends to be relatively wasteful, right? So first, you have your pre-process step for reflection information gathering. So you'll run your libclang on essentially all of the headers, and then you'll just analyze the AST a little bit, expose your reflection data, and then you'll just throw away the whole AST for the compiler to then go around and have a proper invocation to actually compile your code and try to reparse everything again. That's fairly inefficient. And again, this requires very deep build integration as well. You need to pass all of the includes, all of the defines and stuff like that. Otherwise, the parser doesn't know what it's looking at. So really, none of these techniques are satisfactory in my opinion. I would like to just have a nice reflection library I can just pull in and just have reflection for my types. Why is that so hard? A compiler knows about it. Why can't I get it? So for that, let's take a look at how the traditional C++ compilation model works, right? I think we're all familiar with this. We have our source file. It includes probably a bunch of header files. It goes through the compiler. We get an intermediate object file out of it. And then a bunch of those get linked back together into our final executable. And if we map out our previous techniques I laid out, they all kind of use this step just before the compiler, right? So we either do the manual parsing ourselves on the headers, or we manually put our type information inside of the source files. But it's all before the compiler, and really, that would be a really nice place to be able to inspect this type information, right? Because after the compiler is done with it, it knows our stuff. It knows our AST, how our structs look. So why can't it give it to us? And well, for the current techniques, it's fairly obvious, right, why it can't do that. Because these object files, they don't really contain our semantic definitions of our actual type anymore. It's more closer to just assembly and fully compiled code. So it makes sense that not a lot of techniques use that. There is a note I'll add, is that there's actually a bit more in this object file. There is some debug information here. So you could try to use that for some reflection techniques. I think you will get somewhere. However, there are some downsides. That is that, of course, the only thing that you will see in this as debug info in this object file and in the final executable PDB, for example, it's only the code that's compiled. So if you have a library that you want to generate some reflection info for, and you just have a bunch of stuff in a header, nothing will be emitted. In addition, all of the template information is completely lost. You only have a fully instantiated template type. So there are some limitations, and in addition, like it's meant for debuggers. So you're never going to get things like additional metadata about is my class reflectable? Do I have some attributes here? Stuff like that doesn't cross that boundary. So instead, let's take a look at how modules are compiled and how that changes the compilation model. And it doesn't actually change that much from this perspective, right? Don't want to take anything away from the effort going on from the CMake and all of the compiler folk. But high level, what it does is it replaces the header with a module interface file. Now, practically, this kind of is the same thing. It's still like our C++ code. It just has a couple of export keywords thrown in the mix. But the nice thing here is that instead of actually including our interface for every single translation unit, reparsing it every time, it gets cached. So it only gets parsed once, and then that result is cached. This is nice because it gives you a nice speed up, right? It only has to, very expensive headers only have to be parsed once. But in addition, for us, it's really nice because we finally have our representation of the semantic meaning of our header, right? This intermediate step, it still contains what we want to get out of our reflection system. It still contains the type data. So let's try and plug in our own step in between, right? We want to put in our generator there because in theory we can, right? We only have a source file. That source file will import a bunch of those module interface files. So there's an explicit dependency from the build system side. There is a point in time where all of the module interfaces, right, all of those header-like files are pre-processed, but before the source file starts compiling yet. The downside is that that's not really exposed, right? There's not actually like a custom build command you can inject at that stage of the compile process. So instead, what you can do is you can manually put in a hard dependency boundary. A straightforward way of doing this, in a very explicit way, is to create a separate target or project, depending on which terminology you use. So we still have our same my project there. This contains all our normal code that we write as humans. And what we added now is we added a separate project. It just depends on our original one. It doesn't contain any source files, it contains ethereal source files, right? They're only going to be generated by our code generator. And because our reflection data, like fake project, it depends on our original. It means that our original is fully compiled in all our IFCs, all of our binary module interface files, or BMI for short. All of those are available to us to be parsed. Now, I thought this was the only way to do it. Then, just like to give a little token of respect to the CppCon community, I was just talking around with some people, and actually, I was talking to Alan Wolf, and he was like, "No, actually, you can inject it here." And I was like, "What? Where? I've seen nothing in the documentation or anything like that." But here's a little hack you can do, and it's quite a fun one, because what you're able to do is in CMake is you're able to override the compiler, right? The compiler that it wants to invoke. So what we can do is instead of compiling directly with our MSVC or Clang compiler, we can redirect it first to our own program. What our program will do is essentially just format the arguments to our real compiler that we want to invoke. But then we have the ability to just do a little if check to see, okay, did we create a BMI file, binary module interface file? Okay, then I'll now do my code generation on it. So that's actually kind of a nice way of doing it as well. It feels a little bit hacky to me, so you can decide for yourselves which technique you want to use for integrating this into your build system. But now that we have kind of an idea that this is how you would implement this in your CMake build process, right? Let's look at how it is actually parsing such a BMI file actually works. So I'm going to take a look at one example. I'm going to take a look at the Microsoft MSVC BMI format. This is called their IFC file. I actually tried to look up what this acronym stood for, and I couldn't find it. But I assume it stands for something like interface file container or something like that. What I can find is a full open source specification of this format that has actively been maintained by Microsoft. And like I think I missed one part before, but essentially this is why Gabriel dos Reis called modules a tooling opportunity, right? It's this exact reason that we can read the intermediate data and we still have like full information of what is going on from a C++ point of view. So, okay, let's take a look at actually parsing this, because it turns out to not be a too difficult of a format, but it's nice to have a bit of an idea or a guideline of how this is traversed. So there's essentially three parts of the file format that we care about. At first, there's a header. This makes sense, most file formats have it, right? It contains like, what is the name of our module, things like that. But importantly, it contains an offset to our table of contents. This is, you can think of it as a map of string to our partition. Now, what is a partition, you might ask? Well, it's essentially an array. It's an array of a specific type. So for example, the IFC spec specifies all of the possible partition types with all of the possible structures. So here, for example, if you would search for the qualified type in the specification, you would see that it is in the partition named type.qualified, and that the structure which is inside of qualified type is first as an index. This index goes to the unqualified type, right? So like the raw thing without any const volatile. And then we have an enum value. And this enum value is like a bit set of if const or volatile is available here, is applied here. So that is cool. So we kind of have this idea of the file format is essentially just a bunch of like arrays with specific types underneath each other. But that doesn't explain the full story, right? Because this BMI essentially is supposed to represent an AST. It's supposed to represent a tree of syntactical tokens or whatever representation we choose. But these are all flat arrays. The way that the tree arises is that these indices, right? So previously, I can actually show you that our type index, right? Our type index is a specific form of an abstract reference or abstract index. And what these are essentially just two numbers. That's all it is. The first number in an abstract index, it specifies which partition you want to look into. So for type, there's a bunch, there's like 15 or something. There's all defined in the enum. So you would see, okay, my text sort, it's a fundamental type. So you would look in the fundamental type partition, right, in that array. And then the index is simply an array in that partition. So that is kind of our reference, like our pointer semantics. So this will connect all of the partitions together into some form of tree or graph, if you will. Here you can see an example of how that would work. So on the right, I have some example code. I have two structs. The UUID is contained inside of the entity. Using the newly released IFC SDK from Microsoft itself, they have a little visualizer on here, which is nice, so I can actually show you something other than code. And here you can see that tree structures is kind of visualized in this way. The way it's set up here is our global is kind of our global scope. So it contains a bunch of other indices to whatever it contains. In this case, it contains a bunch of references to even more scopes, right? Classes and structs and stuff are actually in the spec, they are still scopes. They have a type that specifies that they are a class, but the actual partition is the same. Then in the scope, obviously, we can recurse again. And then we can see that for our entity, for example, we have a bunch of things which are called fields, field declarations. From there, you can get things like the name, you can get, again, the type of that specific field, and you can kind of keep going. I won't exactly put a scanner or a parser like this on screen, but I hope you can get the idea of how you would write a recursive parser through such a structure. Instead, I'll give you my own library that I wrote over the course of like a year or something. And I call it Neat Reflection. And that's because I believe that this is the first time that there's a reflection library that can neatly integrate into your projects and do it in a way that I find sufficient. So It contains a neatly implemented runtime reflection library. So it has the ability, so it essentially has all of those type erasure parts I'm going to talk about later. Just, it's good to know that it's in there, so you can always look back for reference about how it all fits together. In addition, it generates the reflection data in a fast way, right? Because we can directly take a look in our BMI files instead of doing a lot of double work and stuff like that. And it integrates nicely in your CMake project. Bless you. So you can use this as a reference. That's kind of how it's meant to be used. It's not meant to be your go-to library to implement everything. It's meant to be a starting point for you to implement whatever solution you want to solve. So it is worth noting that even though it solves the downsides that I mentioned before of the previous techniques, it has some limitations of its own. So I'm going to quickly go over those. Naturally, the first one is that it requires modules, right? This is the compile step that I was relying on. So if you don't have modules, I cannot reflect those. The other one is that even though the IFC format, it has a very extensive specification around attributes. It is able to represent all of the types of attributes that you want. It doesn't actually expose the things that the MSVC doesn't understand. So if you want to use your own custom thing, which I want my class to be reflectable, or I want my class to be serializable, but not this field or something like that, it will actually just be stripped out. It won't show up in your IFC, which is a real shame. And I'm I put up a ticket to see if we could get this into the IFC file. And the final one is that it is really nice to not have deep build system integration, right? All we need is that single IFC file. The only problem is we do need to get that IFC file. Typically, in CMake, you're able to query those things fairly well, right? You can query wherever the DLLs are going to be located, all of the OBJs that are going to be generated, PDVs, all of that. But modules are a bit different. They don't expose it yet because it's new. And for two, I assume that it's going to be a bit of a challenge because it's going to be a lot of dynamic file path stuff at runtime because of the dependency scanning. So there are some things are not just growing pains about a new project. There are some things that I think will keep being difficult. So the first one is that templates inside of an IFC are not actually instantiated. So it means that if you find a field which has a type that's like a stud vector of int, you will just see syntactically there's going to be a stud vector and the first argument is int. And all the instantiation you have to do yourself. This is nice in the IFC file because it keeps it very small, but it's very annoying for us because it means that now we have to kind of implement a sort of parser that understands a lot of C++. And as you know, especially with a bunch of the meta programming talks that have been here today, that is insanely complex to do. The saving grace for this for reflection is that you can still use it fairly fine. Around like 95% of code is fairly normal. And you're able to, MI scanner, for example, it just has a bunch of boundaries of if you start using templates that depend on concepts for their specializations or stuff like that, I just don't reflect that specific part of the type or that specific type, but it can still parse all of the rest, right? So you get most of the information that you still care about. And the last one is that it is kind of compiler specific, right? I just explained to you the format that MSVC uses, but other compilers have chosen their own formats. So this is kind of where I want all of your guys and girls help with. If you know how Reclang works, how their AST gets serialized for modules, how GCC works, I've never looked in the GCC code. Please try and see if you can extract some information about that as well. There is a push from Gabriel dos Reis. He published the IPR, the Internal Program Representation Project. This is supposed to be a compiler-neutral representation of such a thing, right? Of an AST, essentially. And if we could all get all of the compilers, all of the major compilers in there, then we could just depend on IPR and we would be able to write a lot of different toolings, even not just reflection, also static analysis and stuff like that, in a nice way. Again, in a very fast way as well. So, okay, with that out of the way, I'm gonna tell you a bit about what I want this library to be used for. Right? Like I said before, it's not supposed to be a fully implemented thing. It's more supposed to explain the concepts, and so you can take a look at what you want to take for your own solution. And for this, I want to tell a little story or anecdote, if you will, because I'm an engine programmer, right? I like writing game engines, doing the low-level stuff. But there's a stereotype with engine programmers that we like to reinvent the wheel all the time. And I agree. I think it's incredibly fun to reinvent something, just doing yourself, learning what's going on. But in addition, I actually think that there's legitimate benefits to writing a solution that is bespoke to your problem, and not just trying to use a generic library, overly generic library, and trying to bend it to your will to do what you want. So that is kind of the setup for my project, right? I have given you the tools to inspect the AST through the binary module interface. I've given you, and in a moment, I'll give you the abstraction tools to write your own runtime reflection project. And you can kind of mix and match those tools however you want to make your Python binding, to do your UI stuff, to do whatever you want. So for the final part of the talk, I'll talk about how the things that you can use to type raise and to influence such a reflection library. So to quickly recap what we had before on the slides, this is what we have, right? We have a hash map of our metadata type, and our metadata type essentially contains an array of fields and methods. So now it's time to actually implement our field abstraction, right? We previously have defined the interface for it, but now let's go to the implementation. So again, I want to first get your mental model up to date about what we're trying to accomplish by writing this piece of abstraction. So the idea is that instead of having our object that is variable, which I think we're all very familiar with, right? Like in this example, we can get any entity, we don't care. Our variable just refers to some entity. And then we can do stuff with it, like create name or whatever. What we want to do is instead we want to reverse it. We want to make our member access variable. So we want to be able to, we have our entity, we know where it is, but we don't know actually which member we want to access at this time. This is what we're going to try to implement. And it turns out there's a very concrete construct in C++. And it's been there for a long time, in fact. This is called the pointer to member. In this construct, you can see a bit of the syntax here. You can see float entity, colon, colon, star. This means that it will bind to specifically an entity type, our entity type, and it will reflect fields that are of float type. How you assign it into that, right? How you gather those fields. So you can use the ampersand of the member. And as you can see, this is a float member, right? So we would just as well be able to assign the X and the Z into here. Then how to actually use pointer member. You can dereference it using the dot star operator. Or in case that your object is of a pointer type, you can use the arrow star operator, right? It's kind of like you're dereferencing the left side, but also the right side. So now that we have an idea, a concrete idea of what we want the implementation of our field to be, let's go and implement it. So remember, we had this interface, and mainly the difficult part is implementing our value function there, right? The other ones are just data getters. So let's first start by implementing it using a fully hard-coded thing on top of our entity class with only integer fields for some reason. The way we can do this is we can actually just store it inside of our class to be assigned later. And then in our value function, the way we access it is again by using that arrow star operator, and then we get access to the reference of our member. So from there, we can do whatever we want with it. We could assign a new value into it. We could return this by value, anything we want. In this case, I chose to return a pointer to our field to be used for anything we want later. So now, of course, we want to use this for more than just my entity class. So let's generalize it using two template arguments. Now we're able to instantiate a field impl for kind of any objects that we want and any field type we want. Cool. And finish it off, of course, with these data setters. But there's a bit of an annoying thing here, right? There's this inheritance chain. It's kind of complicated. All of them at runtime need to be allocated somewhere. There's going to be some pointer chasing. And all that we really need, all of the data that we care about, is all same. Most of it is same size, right? The only thing that is not same sized is our pointer to member, which depends on some of our templates there. But it would be really nice if we could move this out of the actual runtime version of our class. And it turns out we can, because just like you can have non-type template parameters, like integers and stuff like that, compile time at compile time, you can actually have the same for pointer to member objects. So we can move this just to our template declaration, and it's fully out of the way of our runtime side. And this becomes very nice, because now we don't really have a good reason to make this a complicated inheritance hierarchy. We just have a struct of data. We just have a name, we have a type, all of that stuff. The only thing, of course, we still need is that we need some type erasure somewhere. There was another reason why we had our virtual function, is to be able to implement our value function specific to the field you're representing. But if you think about what our virtual call was doing, it was not really magic. What it was actually doing is it was following some vtable pointer down to some static memory, and that contained a bunch more function pointers. So actually, we can just do that ourselves. We don't need inheritance for that. We can even inline it to avoid one extra interaction, which is cool. So what we can do is we can define a signature for our function that we want to type erase, essentially. And then we can have a specific implementation of this with a bunch of templates. So at the time where we're going to instantiate this field object, we can also instantiate a specific version of our function and then assign a pointer into our value function field. And this is very nice. It's kind of like these two techniques work together with type erasure very well. The same goes for methods. I won't have time to implement all of or to explain the full method template implementation of actually calling each parameter and casting it and passing it on. Just know that at a high level, what we're trying to do with this function is that we have a bunch of arguments that we're going to pass through a type erased interface, right? So we have a span of a bunch of void pointers. Then in our implementation, we know exactly what those arguments need to be. So in this case, I don't know any validation. You should do validation in your own implementation. It's in my library, of course, but the slide has only so many pixels left. And then for each of those arguments, we grab them out of the span and then we cast them to our correct type. This requires a little bit of a helper function and passing an index sequence so that we can have 0, 1, 2, 3 as indices that we can index into our span. If you want to look at this later, I recommend doing so. But in general, you don't need to understand this to understand the talk. So that's actually it. That's all that we need to do for our reflection library. It's being able to abstract, like create this type erasure interface, and kind of having the understanding of how pointer to member works, and that you can even put it inside of your template declaration or template signature. So there are a couple of other things that you need to know to implement a full reflection system. So I'm going to quickly go over those. So one of the things you probably want to do is you want to be able to create objects. Right? From your metadata type, you want to just instantiate them. For this, you'll need to know the constructor and the deconstructor. But again, we'll use the same type erasure technique as before, have 3 functions, and then in the case of a constructor, we use placement new to invoke the constructor. Deconstructor, you can manually call that, like shown here. You also probably want to have some special API dedicated to container access. So things like a vector-like interface and things like a associative array, like an unordered map interface. The reason why this is kind of almost necessary is because a lot of the APIs that we define today in C++, they are not actually concrete, right? If you remember, if you look at how a normal way is to insert things into an unordered map is to use the inplace function. But the inplace function doesn't actually exist because it's templated on whatever you give it. So you need to explicitly instantiate it for whatever interface you want to provide. In addition, you are going to want to associate a template type that you have in the compiler with our runtime value. Essentially you need this to be able to implement something like a get type, so that you can do like remember that serialization example. I had all of these statements like, oh, if my type is equal to the int type, or if my type is equal to the double type, you need to associate your template type with something that you can reference at runtime. So there is a way to do this in standard C++. You can use a type ID operator. And this works quite well. However, generally in the games industry and in embedded, these are turned off because they tend to bloat the binary unnecessarily and are just generally not fast enough for our purposes. So it's time for a trick. I call this the template type ID trick. And the way it works is in 2 steps. The first one is obvious. It's to create unique numbers. The easiest way to create unique numbers is you have just some counter somewhere and you keep incrementing the counter. So every number you return is unique. Then the second part is our actual implementation of the type ID. And that is it looks actually very small. It's kind of neat in a way. You call your generate unique number, then you just assign it to a local static and then you return that. And then the first time I saw this implementation, I wondered how this did anything. Because my static here, because you were just calling functions, why is this creating a consistent ID per type even? And the explanation is in 2 parts. So the first part is local statics are lazily initialized. So the first time you call this function, that is when we're going to create our unique number and store it inside of our local static. And the other thing is that because it's lazily initialized, it's never going to be initialized after that. So if you keep calling the same function, it's going to give you the same ID. And that is nice. However, there's going to be all kinds of instantiations of this function, right? How is it going to work together? Well, the linker helps us in this case. It will make sure to deduplicate all instances of this getID function per type. So effectively, we'll have only one getID instantiation in our whole program, which means only one local static, which means our unique number. So this is nice. It gets us where we want to be. It does fall apart with DLLs, but to be fair, so does the built-in type ID operator. And it is technically call order dependent, right? If you first call the getID of int and then you call getID of bool, you'll have a different ordering. You have a different number at runtime. But we don't really care about that. All we care about is that at this runtime of this specific instance, we're going to get consistent numbers throughout the program. And that the other one is that it's not a const expr. And this makes sense if you look at the local static, right? It gets assigned at runtime. It means it's not const expr. There's a way to fix that. You can use, instead of locally storing a number, you can take an address to some part in memory. So in this case, again, the linker is going to help us deduplicate all of the instances. So we're only going to have one pointer essentially per type. So this is nice. This gives you a const expr variation. However, it does mean that the ID you get back is quite big, right? It's a pointer size, which usually nowadays means 64-bit, which in my opinion is extremely overkill, because by the time you have over 4 billion types registered in your reflection system, I think you have different problems. And now we're going to go over to one of the final parts of our reflection library. We want to be able to represent base classes, right? So we can have an inheritance hierarchy. So to implement this in our runtime, it's trivially simple. We just store an array of again these type IDs, right, that I just explained. We just store an array of these IDs. This will of course lead to a reference to the base class, and then those have a similar, they have the same list of base classes, right? So it forms a tree, an inheritance tree. Now, to actually use stuff I'll start again. To actually use our reflection library, we need to be careful with slicing. So here, if you take the example of base A, base B, and then those together combining to C, you can imagine that the way that's laid out in memory is that first there's going to be int A, because it's just the first one that shows up. And then you're going to have int B. This means that if you want to call the function on base B, you need to call it with this pointer essentially at the start of our base B, not at our concrete C implementation. So you need to do essentially offset the this pointer to be at the start of our base type where we want to operate on. Now there are a couple ways of solving this in our reflection library. So one of them is the simplest one, and it's more of a brute force approach. You can let every class store all of the fields and all of the members of all of its derived, of all of its base classes as well, right? So you let C store A, B, and func still. This of course leads to a bit of duplication because you'll have derived types copying essentially implementation of each of the fields of the base types, but it means that the C++ machinery will do the offsetting for you, which is very nice. You can also do this offsetting yourself. So one possible implementation of this is to use this rebase pointer function. The idea here is that if you have a concrete type pointer, they cast it to the base class, both of them are known at compile time to be base class of each other. It will do the offsetting for you. So here you'll see it will return a different pointer if it has a different offset. In this case, it will also still work with virtual inheritance. However, I will highly recommend just not using virtual inheritance for your reflection library. It will just complicate things a lot for, in my opinion, not much benefit. There's a way you can do this without calling a function, right? Because now you need to do this function for every single class you have with every single base type, which is a little bit wasteful. You can also try to do this at compile time. You can do a similar offset off trick where you start with a C pointer that's assigned to 400, and then you cast it to something. You get the result from there, and then you subtract that from your original 400. Then you have the relative offset that those two classes have together. However, if you do that, you need to be extremely sure that you're not gonna have any type of virtual inheritance, because then obviously that offset doesn't work at all. Okay, so I hope this gave you a kind of an overview of how you can implement the reflection system using stuff that's available right now, like using modules, and ways of implementing your library and hopefully solving your own problems. For your own problems. So thank you all very much for listening and showing up. Are there any questions?
Is this work?
Well,
Hey. Oh yeah. You mentioned that there's this IPR proposed to standardize the representation. Have you considered maybe in your library implementing things against IPR and then create like a converter from specific compilers to IPR?
Yeah. So I have considered it. The problem with it is that when I first started the project, I knew nothing of the IFC format, right? So I kind of felt like I was putting the cart before the horse, trying to implement the reflection library, and then at the same time, before I even started the reflection library, I was going to make an abstraction about a format I didn't know about. So that's why my library is tied to IFC currently, in this release, obviously. But yeah, I can see myself writing a converter, definitely for the MSVZ version to IPR. Because it would be really awesome to just write my program like the parser the parser you'll see. If you look at in my library, it's not too complex. It's essentially just like a bunch of recursion, just going up the tree of possibilities. So if I'm able to do that with IPR, that would be absolutely awesome.
You had called out a downside of needing to create modules before you could reflect on them. Have you taken a look at header units to just simply throw the headers that already exist to generate IFC?
That is possible as well. It does mean that, of course, you still need modules, right? It's just that your translation unit that's going to be importing it as a header module, that one needs to be C++20, and that one, in my definition of modules, uses modules. But yeah, you could probably do something like that. I think the IFC format also, if I can remember correctly, it will store them in the global module fragment. So it actually does show up in the file for you to reflect stuff.
All right, thank you for the talk. Besides the name and type of members, do you have other what access it is or virtual function, stuff like that?
You have everything. You have absolutely everything, with the exception of, like I mentioned, the user attributes. But even attributes that the compiler doesn't understand, those are even emitted. So if a function is no discard, you'll be able to see that. And yeah, same for any access modifiers, anything like that. Yeah. All right. Any more questions? Okay, then I want to thank you all very much for attending. It's been a blast coming to CppCon, so thank you all very much.